And now move this one.
Yeah. Yeah, sure.
Hi everyone, welcome to the ICTS String seminar. Today we have Mritunjay Verma from University of Southampton, who will be talking to us about scale invariant effective field theories in AdS.
Thank you, Anupam. It's good to be back here.
So I will talk about some work which is in progress. It's about scale invariant field theories in AdS. And this work is in collaboration with Kostas Iskendaris and Vidisha Chakravarti, both of whom are in Southampton. So let me begin with some motivation why this is interesting. So we all know that conformal invariance plays an important role in our current understanding of the fundamental physics. And the conformal group is made up of Poincare scaling and special conformal transformation, as we all know. So these are the transformations. And an interesting question to ask whether there exist non-trivial theories which have invariance under just scaling and Poincare transformation, but not under special conformal transformation. So we can ask if there are theories which are invariant only under these two transformations, but not under this one. And the answer to this question had some important implications, and let's consider some examples. So in string theory, the consistency of the worldsheet theory requires conformal invariance. However, the target space-time equations are obtained from the vanishing of the worldsheet beta function. And the vanishing of beta function only indicates the scale invariance. So this means that if scale invariance were not enhanced to full conformal invariance, we could in principle obtain inconsistent string background. So we could obtain backgrounds which satisfied the conditions which followed from vanishing of beta function, but they would not be consistent with the quantum theory because they were not conformal. Luckily, this is not the case. And similarly, another example from condensed matter is that the critical points in condensed matter are defined by scale invariance, but their classification is done using the full machinery of conformal invariance. So here again, one assumes the enhancement of scale symmetry to conformal symmetry. So this issue has been settled in 2 dimensions. If a 2-dimensional scale invariant theory is unitary Poincare invariant and has a discrete spectrum, it must have conformal invariance. And of course, one can construct scale invariant field theories which violate these assumptions in 2 dimensions. In d equal to 3 and d greater than equal to 5, one can construct unitary scale invariant theories which are free Maxwell theories, and these are not conformal. But even in this case, there are it is not clear whether one can have more non-trivial theories. In d equal to 4, there is no final verdict on this. There are perturbative proofs that near a critical point, the scale invariance gets enhanced to full conformal invariance. There are also arguments that this should hold beyond the perturbative regime. However, there is no complete proof for this or any counter example yet in d equal to 4. And our goal will be to analyze this using a specific example in the context of AdS CFT. Another motivation for this work actually, which got us into this problem, so it comes from the application in the context of inflationary cosmology. So to describe inflation, we don't have like some UV complete theory. So what one can do is one usually writes down some effective field theory to describe inflation. Now, there are parameters in this effective field theories, and one would like to fix those parameters. I mean, one would like to find a bound on those parameters. And the implication of unitarity and causality on the Poincare and conformal invariant theories have been studied extensively in recent past. And demanding consistency with the unitarity and causality impose certain restrictions on the parameters of the effective field theories. However, these constraints are not directly applicable in this inflationary for the effective field theories which are used in inflation, because the time translation symmetry is broken there. So how to fix the this parameters in effective field theories describing inflation? So one way to go about doing this is to use AdS CFT. So in AdS CFT, one can map inflation to a boundary problem of RG flow, and it turns out that the RG flow in the boundary theory, it is related to the breaking of radial translation symmetry in AdS, and one can write down the effective field theory describing the Goldstone mode associated with this breaking, and one can map this effective field theory to the effective field theory of inflation if we interchange the de Sitter time with this radial time. So at the level of effective field theory, if we get some constraint in AdS, we can hope to apply it to de Sitter cosmology in the inflationary background. However, it turns out that this setting comes with puzzling theories which are scale but not conformal invariant. So, one way to see this is that inflationary correlators are approximately at the leading order, they are scale invariant, but inflationary background breaks the conformal symmetry. So what it corresponds to in boundary theory is a kind of question one would like to know. So the so okay, can you repeat again? Yeah. Yes. Right. Yeah. Mm-hmm. Okay. In particular, what happens in that is that the metric itself, which in AdS, the metric is not dynamical, now becomes a dynamical degree of freedom on the defect size. And indeed, if you choose some gate choices, that preserves scale invariance but not conforming. But it's not something that would be visible directly in the AdS CFT calculation, but only when you do this additional step of squaring and integrating the function. But then it implies the existence of scale invariant theories which are not conformal. This is what you are saying. It implies that. I mean, they're not the theories because they're not the action for these theories is not local. Okay. But okay, here we will have like some specific theory, and we will try to analyze whether they indeed have like the bound. Can you have like specific boundary conformal field theory which can be just scale invariant? Cosmology, I will not come back to it. So because we have not gotten still at that point. So because still there are some puzzles in just in AdS. So the brief outline of this talk will be, so I will first describe this effective field theory in AdS. And with which we shall be working, and then I will analyze the word identities and anomaly in this theory using the procedure of holographic renormalization, and then I will consider the 2-point function by using linearized analysis, and then show that it's not consistent with what the solution of these effective field theories have. And then I will describe something which is known for some time, the Einstein-Horndeski theories, where it is claimed that there exist scale invariant theories which are not conformal. But then the puzzle arises because we can map the two theories by a field redefinition, which I will come to in the end. So let's begin with this effective field theories. So the most general 4-derivative effective Lagrangian, which describes an interacting theory of gravity and a single scalar, is given by this. So what one can show is one can try to write down other terms, but then one can, by using Bianchi identity and integration by part, one can relate it to combination of these terms. So this one can show that this is the most general effective field theory one can write down at the level of 4 derivatives. And so this is the standard Einstein-Hilbert term. Then you have the kinetic term for the scalar, and then B is the potential, and then you have these 10 parameters. So all these F1 to F10 are high derivative terms. This one is F10 is a parity violating term, and it's okay. So this is only in 4 dimension. In other dimension, there might be other terms, parity violating other terms. MP is the Planck mass, M is parameter, and C here. There are 2 terms involving the C mu nu rho sigma, which is Weil tensor. So in order to avoid the unphysical degrees of freedom from becoming dynamical, we need to treat the high derivative terms perturbatively. And in particular, we should make field redefinitions and eliminate those high derivative terms which are proportional to lowest order equations of motion. Otherwise, we will find that there are gauge degrees of freedom, dynamical gauge degrees of freedom, which we don't want. And this field redefinition allows us to eliminate most of the terms in the Lagrangian, and we are in fact left with just a very simple looking Lagrangian. And actually, Weinberg used this Lagrangian to study effective field theory in inflation. So we shall still simplify our life. So we shall specialize to the shift symmetric scalar fields in the bulk, and this implies that coupling FIs are field independent. So these, to begin with, these coupling F1, F9, F10 are field dependent in general, but we shall consider the shift symmetric theories. So for them, these FIs should be constant. So we shall consider these FIs to be constant. And further, we shall use the fact that the Weil tensor vanishes in AdS. And since the terms involving Weil tensor are quadratic, so all the equations of motion will always involve a Weil tensor, which will vanish in the AdS background. Hence, for our purposes, we shall forget the Weil tensor terms, and it will not change any of our conclusions. One can keep track of those Weil terms, but it will not be needed in our analysis. So the action. Yeah.
Normally, we have the scalar or you set the scalar to a constant. You have there are 3 R squared kind of terms. You can write one as Y squared. One.
Oh, you mean in the anomaly?
No, just in the higher level.
Okay.
There are 3. Either you write a scalar square or u squared, curvature, tensor square.
Yeah. So
or
let's.
some combination which is Y square, curvature square,
yeah.
and Y square, Gauss coordinate,
yeah.
and maybe one more. In that case, you can eliminate one of them by field redefinition of G mu. One of them, it's a total derivative in 4 dimensions, the Gauss coordinate, and that's why you're left with only one. But here, when you have a scalar, then the Gauss coordinate term is not the total derivative.
So, but now we have this Weil square term.
But that is some linear combination of curvature square.
So, in fact, I think what you are saying, it's possible, but one can translate it to this language and.
No, that is the parity violation.
No. This will have, okay, I mean this I mean this term, F9.
Yeah, so here at this level I see that there is an R square, R mu, and Weil tensor square.
Yeah.
And then a parity violating, which I'm not considering.
Yeah.
Okay,
Right.
But then your next step, when you set the field redefinition, you can eliminate most of the terms and you're left with only one.
A Weil square.
Yeah. So I'm wondering why you have only one and not 2, because one is what you would have had in the absence of the scalar.
Yeah.
Because there would be a Gauss coordinate term, which would be a total derivative. But if you have a scalar, then you can have a function of phi times the Gauss coordinate, which is no longer a total derivative. So.
Okay, I think. Okay, let me think about this. I think, but I think it's possible. one survives here. I will come back to this field redefinition later in more detail, where I will give the explicit field redefinition, which takes us from here to here. You mean F1 term? Yeah.
But that is just a kinetic term.
No, this is not kinetic term. Yeah, square. Yeah.
The equation of motion.
Yeah, I think this is how it works. But okay, I have not done the calculation in that way. I mean, but
this is Weinberg's result.
yeah. So as I was saying, so we shall also forget this while piece, and it will not change any of our conclusion. So the action we shall be working with is just very simple, this action. So we have the kinetic term, Einstein-Hilbert term, potential, and this square of kinetic term. And then we have also added this Gibbons-Hawking-Yark boundary term, which is needed for the correct variational problem. And also it plays an important role when you do holographic renormalization. And the equation of motion of this theory one can... so while square term usually, so it will so equation of motion, so because it's quadratic, so equation of motion will always involve one while tensor, but since we are in AdS, it vanishes. So and later we will also study the linearization of this action. So when we consider linearization, so when we vary this term, it will always be multiplied with 1c, which will vanish. So in AdS background, it's not important. For the purpose we are interested in. So now this theory admits the standard conformal vacuum solution. So yeah, where phi 0 metric is standard AdS metric, and potential it is just the cosmological constant term. But it also admits a different AdS vacuum where the scalar field is logarithmic. So it goes like some alpha log rho, where alpha is some constant. Rho is the radial coordinate, and the metric in this coordinate is this one. So this is the metric in the Fuhrman-Graham coordinates. And in this vacuum, this coupling F1 and V gets fixed to be this. So these are special points in the coupling space. And so for these parameters, we have a different solution, which is AdS. But now, due to logarithmic scalar, the full conformal symmetry is broken to just Poincare and scaling. So we no longer have spatial conformal invariance in this vacuum. Now under scaling, the scalar field will shift by a constant amount. So if we do scaling, say rho goes to lambda rho, then this phi of rho will go to alpha log rho plus some constant. But since scalar field in our theory only appears through derivative, so the vacua with phi x and phi x plus c are identified to be the same vacua. And the boundary theory of this vacuum is expected to be a scale invariant theory, and our goal will be to investigate this. And the things we would like to compute are the anomalies and the two-point function of the boundary operator dual to the scalar field. Due to UV divergences, the boundary correlators in general diverge, and in the bulk side, this is taken care by the procedure of holographic renormalization, to which we shall turn next. Okay, this 1 over xi, okay, this 1 over 6 are.
I don't know whether it works for these higher derivative terms, but is it possible to have a conformal coupling so that, because under a conformal transformation, that background phi goes to
phi plus c.
We'll get some shift which will be x dependent.
Yeah, that will be x dependence. Yes. So
maybe there's some conformal coupling possible, which will
So you,
that contribution.
so it's like making this alpha x dependent. It will be, or
Yeah, I mean, rho will go to rho.
rho plus something. Yeah.
Rho multiplicative.
Yeah, yeah, yeah.
Rho will go to rho times some
Yeah.
factor. So it will shift. 5 rho will shift to. You'll get an additive piece which will depend on.
No, x. Okay. But this will be like gauging the shift symmetry. Or
Particular kind of, like not only the special conformal transformation,
Mhm.
not all.
All
So I
right.
thought
Yeah.
so the question is whether there's some arrangement of derivatives such that
It can.
the derivative terms of the scalar such that it cancels.
Okay, you mean the conformal transform? Okay.
No, so under a ordinary scale, phi gets shifted by a
Constant.
Under a special conformal transformation, phi will get shifted by something which is a function of x. But it will be an additive shift.
So you want to cancel this, right? Yeah.
It won't be there. But I'm wondering whether, but it will be some special functions of x, like the ones corresponding to the special conformal transformation. Just wondering whether there's some this thing of the, because there are derivative terms which will give you contributions, whether you can cancel off the derivative terms, because after all, in a way, you only couple scalar also. Isn't that what you do? You modify it's a special conformal transformation. As you said, the phi of x plus some rho of it will be plus some alpha of x.
But is that a solution? If you just do a, so there's a quadratic transformation. There's a diffeomorphism corresponding. There's a special conformal.
Yes.
Diffeomorphism. Yeah. If you do a diffeomorphism, the original equations are diffeomorphism. So you should get another solution.
No, so special conformal transfer, another solution meaning yeah, isometry. Yeah.
So the isometry on is fair, but no, like 5x also should be a solution of the equation.
But
either the if you're what you're saying that the factor is not invariant, then you should get a model space of solutions which are related by special conformal
transformations.
So is that what you get a full model space?
So I mean, we have not analyzed the like this moduli space you are saying. I mean, which are related. I mean, so different vacua. So we are still like okay.
You just apply the special conformal.
Yeah. Yeah.
A square is invariant. Phi will get some phi. So but that should be a solution because it's a diffeomorphism. Okay. It's probably a large diffeomorphism, so it's not like a gauge transformation, but it should give you a solution. I mean, rather than say that it doesn't go to zero at about so hence it acts on the boundary theory. So it's actually symmetry of the theory rather than gauge.
Yeah.
So then you should get a new solution.
But it will. Yeah. Go on.
One way you get around this is if you're somehow saying that the solutions you're identifying by using some framework, maybe that's just some definite coordinates, and that form is also replicated by special conformal transformation. So that's an isometry of deviation.
But I mean this logarithmic scalar breaks this special conformal. Okay. Yeah, rho is the radial. Yeah.
Yeah, rho will go to rho
But then if you get a model space of phi, where the metric is invariant, but you have a model space of phi, solutions of phi. They're all solutions of the differential.
But all of, I mean, so, but all of them will violate this special conformal.
Yeah, but the conformal translation will kind of translate this model space of solutions.
Okay, I see.
So like that's it's like spontaneously.
Okay.
So that's a
but the problem with the others is that they break also the background on the boundary is very rotational. Right? I will be a function.
have you gauged the shifts within the
No.
Like not gauge the shifts.
No.
But those that can be absorbed.
No. Those are your solutions, but that solution will have a function of x. So then you will be breaking more than.
So this phi of rho, the alpha macro is a normalized. Assuming you can get a normalized.
But it will have a function of x. Right? Like you said, the solution will be a function of x. So those solutions will break the background.
So you get a special conformal bootstrap. These are different theories, but it's like have if the boundary theory is scale invariant but not conformal invariant. You make a conformal transform. It's not a symmetry. You give another theory. So that's why the boundary is scale. This will get by this one. Yeah. I think it's not clear. It's a different theory. Maybe
it's a question of what boundary conditions you demand for phi. If you insist that phi has a form A plus B log rho, then none of these solutions have that form.
I mean, the question is then you in the model space, you look at the phis. Either change the normalizable change or non-normalizable change. If it is non-normalizable change, it's not normalizable.
Yeah.
A plus B log rho is the general one.
But if it's not,
this will be A, which is a function of x. So as a row dependence, it's normalizable. So only the x dependence it will be.
So if it is normalizable change, it should really be interpreted as a state of the same.
But it will be a state which breaks.
Yeah. In different states. So it's a good stone excitation. Because the spontaneously broken extension.
So I don't know if you mean normalizable. I mean, phi here is you could say that the boundary value of phi is the parameter that you it's not what we usually call the normalizable fluctuation of p. It's the constant mode of the p.
Constant is a subdominant.
Log rho is the denominator. Log rho is the denominator, and this is the one term. Yeah, so this is the next. Now I don't know if I guess he's fixing it. He's saying that should be a constant in the independent of space. Then the other solution.
Yeah.
Also, as Ashok said, from the AdS background part of the thing, which is normally the whole action is not doesn't have it has
It is a multiple if you want to.
Yeah, so we're saying this whole solution has one more solution where the metric goes to itself.
Phi goes to 5 plus 9.
5 plus 8 or 6.
Part of the action is
The common transmissions are just different ones.
they're not special.
Yeah.
There's isolation.
Yeah, they're isomet.
Your operations are just big.
Oh, no. This G is the metric. Yeah. I mean, I'm denoting metric with the capital G. Yes. To alpha log.
And this is the answer to the question that you know,
Invariant. Yeah.
which has also this negative constant.
But you want to consider? No. So later, I mean, we will consider the linearized fluctuation around this solution. So that that will change the from pure AdS to something else. Yeah. Yeah. But yeah.
Maybe that's the point that I should be saying. If you make this change, once you back the angle metric, then you're not going to get this.
Yeah. So when we do fluctuation, then I think the metric will change. So this is only in this background. I mean, for this particular value of phi that we have the exact AdS of these equations. So you can verify that if you substitute this metric and this phi with this value of f1 and b, then these equations are satisfied.
So including the finite time.
Including the finite time. So M Planck is just G Newton. Yeah. Yeah, no. This is exact solution. So this background solution. Yeah, diffeomorphism. Okay, arbitrary diffeomorphism. I'm not sure, but if you consider isometry, it's just like transfer. Okay.
Because it's a diffeomorphism which doesn't go to zero at the conformal. Special conformal calls are conformal, but diffeomorphisms don't go to zero. So they will actually in general either leave the metric invariant or leave the full state invariant, or they will reduce it. So if you're saying that it's not invariant, then you should be using the full model space of states.
And then you are saying that one should be able to do go from one to the other by this special conformal transformation. Okay. Yeah, I will check this. Yeah, alpha is just it's some it's just some constant. Fixed, in terms of alpha, yeah. Yeah. Then we have a solution, yes. F1 was, I mean, it was the coupling in front of this quadratic term, and V just potential. So V will be just cosmological constant in the conformal vacuum. No, but if you have this logarithmic scalar, then the equations are not satisfied for this V and F1.
So you just make a diffeomorphism.
Yeah.
By the isometric of AdS phi. The AdS phi metric doesn't change. Phi changes. So that is a new solution. Right? The diffeomorphism, of course, is when you are making.
Okay.
You will get this whole family of solutions by this.
By this method, yeah.
I mean, if you take alpha to 0, keeping f1 fixed,
yeah,
you get that. Take the solution. Then alpha to 0.
Yeah, then.
So then x square changes.
Right. Yeah, I mean.
You don't have to set alpha to 0. Keep the solution and just make the change. You get a new solution which has I equal this plus some function of x. And that should also be an exact solution of the equation.
So, I mean, here we will be analyzing the theory around this vacuum, but okay, I mean, I think what you are saying, it will be going, I mean, away from this solution, I mean, this particular vacuum. So that's, Moduli space, yeah. So yeah.
In fact, if you analyze the linear expectations about it, you see the moduli space.
That zero mode of. So I will come to that. So because there is a very interesting thing. So okay.
So from this perspective, it looks like that the symmetry that the special conformal transformation is only spontaneous, not explicit.
Okay. Okay. So you are saying if we are moving in moduli space of solution, yeah.
Moduli space is not really defined theories, but defined solutions in the sense.
Okay. Yeah.
What's the scale invariance is
so we can make just the scaling like x going to lambda x, rho going to lambda rho, and then we see that okay, phi shifts by some constant amount. Yeah. So because this all the terms here depend on the derivative of phi. So phi, it seems it has like a shift symmetry. Yeah. So this is what. Yeah. I mean.
So for example, AdS phi plus S phi.
Yeah.
Diagonal.
Mm-hmm.
Suppose you can set it anything.
Yeah.
For axial.
Mm-hmm.
Okay, but that actually changes the element of phi to G square.
Right.
It's actually different here.
Mm-hmm.
If you shift.
Okay. Yeah.
But I don't know whether that's what happens.
So I. Sorry. Yes. I mean, yeah, it will be gazing. Yeah. So we are not gazing it. I mean, so actually, yeah. I mean, so my analysis will not be like okay, analyzing this moduli space of solution. So I will be just focusing on this particular vacuum for now, and analyze the linearized analysis around this vacuum. But I think, yeah, it's an interesting question. I mean, maybe, yeah, it's a good way to look at it.
I mean, if you just take a complicated state in AdS, generally in AdS here, right? If you apply a special conformal translation, you apply the special conformal translation on the corresponding statements. Unless it's a primary or something, it will give you something. So transform into some of this.
Right.
Some of the normalized. It's just a non-vacuum state.
is whether you get another solution in this theory for phi set.
Yeah, that I think is not possible, but okay, it's let me. Yeah. Sorry? No, no, no. You can. If you, yeah, I think if you change alpha also, I mean, the solution exists. So it doesn't play any role. Negative, yeah, negative or positive. So phi equal, okay, setting phi equal to 0 will be like setting f1 to infinity.
Go back in the
Oh.
I think that you have say for and this as
Yeah. Yes. Yeah, so but that is the this standard solution. Yeah, so here it is true for any f1. Yes, okay, yeah. That I think is possible. Yeah. Different cosmological. Yeah, the L will be different. Yes. Yeah. Yes. Yeah. I think there is a. I think yeah. I mean there is a domain wall. One. No, I think. Yeah. Yeah, it will be related by some domain wall.
yeah, some flow.
Yeah.
It's not a different state in the cell.
No. Yeah, I think no. I think we analyzed, I mean, this particular case, I mean, by a domain wall. I will not be discussing that, but there is a like a domain wall solution interpolating between these two in this for these values of this. But actually, there also there is slight problem that we find that there is a discontinuity at the midpoint when we interpolate between these two solutions.
So that this solution here, the cosmological constant of this is the same as the root.
You mean in this one?
Yeah.
Yeah.
The same.
Yeah. Yeah. Yeah, alpha, yes. But okay, yeah, I mean, so I'm not saying, yeah, alpha is playing, I mean, okay, I mean, alpha is parameterizing these different values of phi, but alpha, you can also set alpha to 0 so that you have a solution for phi equal to 0 and phi with this behavior. And then there will be like some domain wall interpolating between these two. So you can have different values of phi.
Normalizable or non-normalizable.
Okay.
So the way it is confusing because V and F4 are parameters of the field, right?
Yes.
So you should have the same value of the parameters.
Okay.
And then compare different solutions.
Yeah. So that, yeah, that is.
Let's say this parameter, the same parameters that you have given in the second. F1 is x squared by 16 alpha squared and V is that, right?
Yeah.
Given that, can you find a solution, AdS solution? What is phi equal to?
Yes. Yeah.
And that will have a different cosmological.
Yes. So different value of like L. Yeah. Length. Yeah. AdS length. Yeah. So that solution is possible.
What is the different value of L?
Okay. So you mean, yeah. Yeah, I think Yeah, when I consider maybe this linearized analysis, then maybe some of, okay, let's see if things get resolved. So let me come to this holographic renormalization and word identities. So to obtain the 2-point function and word identities, we need to first derive the 1-point function of the boundary operators in presence of sources. And the AdS CFT prescription for the 1-point function of boundary operators is this. So on-shell value of the bulk theory in the supergravity approximation acts as a generating function for the connected correlator. And phi 0 is the boundary value of the bulk field phi, which will in general be dual to boundary operator O of x. So we want to compute this quantity, and for that, so the naive on-cell action is divergent due to this contribution from the boundary, z going to 0 region, or it's actually rho going to 0 region. And this is, as is well known, IR divergence from the bulk and UV divergence from the boundary point of view. And for computing the 1-point function, we first need to regularize the bulk on-shell action. And this is done by analyzing the near boundary behavior of the bulk theory. And as a first step, we need the boundary solution for the metric and the scalar field. So we start by writing the metric of asymptotically AdS spaces in the Fuhrman-Graham coordinates. So if this Gij were eta ij, it would be the exact AdS. So Gij at rho equal to 0 is the boundary metric. And we shall take the scalar field now to have this form. So we will consider now perturbations over this background value alpha log rho. Which one? Yeah. Mm-hmm. So by while term you mean the? Oh no. So that will be actually it will still not be relevant. Yeah. But for near boundaries behavior. Yeah. I mean, if you were considering like quadratic, then, but C vanishes. But yeah. But C will vanish in AdS. Yeah. Yes, but okay. But will not it be like so when you vary this term, so it will be like say delta C times C, right? And then that extra C will make this term vanish. Yeah. Oh, okay. Yeah. Okay. Yeah. Okay. Yeah. Okay. Yeah. So okay, we will not be considering this term. Yes. Yeah. But I think okay, you are right. It will be. Yeah. Right. Yeah. Yeah. So yeah, I mean so you can consider. Okay. So our analysis will be in this theory. Yeah, last term is Chern-Simons. Okay, yeah, this term you mean. Yeah. Yeah, but okay, I mean, if we are considering shift symmetric theories, then okay, it's. Yeah. Okay, yeah. Yeah.
Oh, F10 is won't be able to.
Yeah.
I guess what he's saying that F10 already become dependent of the shift symmetry before you start making those solutions.
Yeah.
For the same reason, F1 becomes independent of
phi. Yeah. So we are taking all these FIs to be constant. because otherwise, okay, there won't be any shift symmetry.
But what exactly is shift symmetry? I used to find the constant symmetry of the lambda. But that's just when the x greater than x prime will be independent of phi.
Yes, yeah.
We'll take them to be
Independent of phi, yes. So one way to look at it is that, okay, we just consider, say, this theory and we analyze the solution in this theory. Okay, let's go. So the near boundary solution is obtained by solving the field equations order by order in the radial variable rho. So for example, to obtain the solution at the lowest order, we set rho equal to 0 in equations and then solve the resulting equation. And this just gives these values of F1 and V. So for these values, if we had chosen already these values, then the lowest order equations of motion, near boundary equations of motion are satisfied. And to obtain the solutions at the next order, we differentiate the equations with respect to rho and then set rho equal to 0. And to obtain the solution at next order, you can differentiate it twice and then set rho equal to 0 and so on. So at some point, this procedure will break down. And this happens at the order rho to the power d by 2. And at that point, one needs to add a log rho in this expansion. So doing this analysis and focusing on d equal to 4, we find that the near boundary solution of metric and scalar field is given by this solution. So you have this, say, for metric, you have G0ij, which is the boundary value, and then you have rho G2ij, then rho square G4ij, then sigma 4 ijx log rho. These are arbitrary functions. And the equation of motions fix this G2 sigma 4 kappa 2, this G2 sigma 4 kappa 2 and tau, this one, in terms of the boundary data, which is G0ij and kappa 0, which are the field theory sources. And the G4 and kappa 4 are not completely fixed from the equations of motion. They only so the equations of motion only determine the trace and divergence of G4ij. This one. So everything else gets fixed in terms of G0, but not G4. Only its trace and divergence gets fixed. And we will see that this object is related to the expectation value or 1-point function of stress tensor. So it's like it gives the web of the corresponding operator, which is dual to Gij, and G0ij is the source. And now, so the full correlator cannot be determined just from the boundary analysis, and this is what it is showing. To determine the G4, one needs to solve the equations exactly away from the boundary. And similarly is for the K4.
So can't it have something like some function of x times log rho in the file?
Yeah, I mean, but that actually, yeah, that one can try, but it doesn't give the so you mean you want to obtain a new solutions? Yeah. Yeah.
But why can't you have a log rho? Have a rho square log rho, but why can't you have a log rho and then?
Oh, you mean here?
The second line, kappa rho x.
Yeah.
Why can't I have something like kappa minus 1 of x times log rho?
So you want to add here rho times so rho log rho. Yeah, log rho. No, so but that you can show that it doesn't solve the equation of motion. So this is actually a general theorem from Fermat and Graham, who showed that general expansion near boundary in even dimension takes this form. So for kappa also, the equation of motion we have, I mean, if you put log rho, you find that it doesn't solve the equation of motion. No. Yeah. Mm.
So you can show that function of x should be
constant. Yeah, 0. Yeah, 0.
guess this is just saying, still looking at this around that new solution.
Around the new solution, yeah. Yes.
So that would be like changing alpha. So which would be on the
Yeah. Okay, so this is just the solution one gets. So like, for example, this G2 is fixed in terms of this G0 Ij, and also R0 is the Riemann tensor computed using G0. And similarly, kappa 2 is given in terms of G0 and kappa 0. Sigma 4 again has some expression, and then you have trace of G4 and divergence of G4. So the explicit form is not important. So next we can obtain now this bulk on shell action, but it diverges near the boundary. So, and we regularize it by putting the boundary at rho equal to epsilon. And we can work out that the divergent part of the bulk on shell action takes this form. So it has terms proportional to like 1 over epsilon square, log epsilon, 1 over epsilon, but and the coefficient A0 is constant, A2 vanishes, and then the coefficient of log epsilon has this form. And this on-shell action diverges as epsilon goes to 0. And to cancel these divergences, we need to add counter terms to the action. And working in the minimal subtraction scheme, one can define counter term to be just minus of these divergent pieces of on-shell action. And expressing the divergent part in terms of the boundary metric. So boundary metric is Gij by epsilon. So if you remember the Performance-Graham form of the metric, so this is the boundary metric. So we can express this counter term action in a covariant form by expressing these quantities in terms of the boundary metric gamma, and one gets this form. And the renormalized action is now defined to be the sum of the regularized action, which is the original action evaluated with boundary cutoff rho equal to epsilon and plus S counter term. And now in the epsilon going to 0 limit, this action is finite. So this is our renormalized action. And using this renormalized action, we can now obtain the diffeomorphism and Weil-Ward identities. So let me just briefly review. So under a change in boundary sources, the change in generating functional by definition is given by this. So CFT is the generating functional for boundary theory, which is given by renormalized action. And under the change, by definition, it takes this form. And now the bulk gravitational theory is invariant under D plus 1 dimensional diffeomorphism, and which is parameterized by xi and sigma. So if we consider the change in the boundary value of the metric and the scalar field under this diffeomorphism, then, so if you consider these changes, so this parameter xi induces this transformation in the metric, and phi is the standard transformations. And similarly, this parameter sigma induces this Weil transformation and on both G0 and G and phi. And demanding the invariance of this generating functional under these transformation gives us this Ward identities. So we want to see that our calculation is consistent with this expectation. So A here is the conformal anomaly, and it now arises because we have done some regularization. So to compare our expression with these expression, which is expected on general grounds, we need to compute the 1-point function of Tij and O. But now that can be computed because we have the renormalized action in our hand. And using these, we can compute this 1-point function of O and Tij in presence of sources, which are given by these expressions. And what one can show is that if you take the trace of this 1-point function here, it is given by this, and now it can be expressed in terms of a 1-point function of this O boundary operator and plus an extra piece, and this is anomaly piece. But this is okay. So this is what we get from the calculation, from the near boundary analysis. Sorry. No, so we have not yet computed the even 2-point function, because so this 1-point function involves this kappa 4 G4, which are not determined from this near boundary analysis. So one needs to first fix this kappa 4 G4 by exactly solving the equations of motion, and then okay, so we have to take the derivative of this 1-point function with respect to sources, but because these are still not fixed completely, we cannot still find out the 2-point function or even any higher order function. Yeah. So here, I mean, we needed that because we wanted to compute the anomalies. But now, since we have gotten the 1-point function, we can now compute easily the 2-point function also by just differentiating these with respect to the sources. Okay. Mm-hmm. So can you repeat again how exactly you are proposing the calculation? So by full solution, you mean the this background solution we had? Yeah. Around that. Yeah. Mm-hmm. It will, but it will be the same thing, right? Yeah. Okay. But can you get anomalies? Probably. Yeah. Yeah. Okay. Yeah. Mm. Okay. Let me come to. Mm-hmm. Yeah. So let me briefly review some facts, what is known about the anomalies. So in general, in D equal to 4, the most general possibility for while anomaly takes this form actually. So the trace of T Ij, T mu nu is given by, okay, one can write down in this form. So first is this while square, then we have Euler density term, and then one can in principle write down this R square term. And for conformal field theory, this R square term, which is proportional to E, it vanishes due to Pesumino consistency condition. When you demand correlator of this while variation vanishes, so that shows that E should vanish. But its presence, if in a theory, if you have got this E, then it indicates a scale anomaly, which is leading to the breaking of conformal invariance. Now, for holographic CFTs in the large N limit, one finds A equal to C. So these two coefficients, C and A anomalies, are same, and that leads to this combination for trace of stress tensor R mu nu minus 1/3 R square. So if we find a coefficient which is different from minus 1/3 in front of R square, it indicates scale invariant field theory rather than a conformal field theory. So one would ideally like to see a coefficient different from minus 1/3. So here we do find minus 1/3. So it seems okay. It's this, at least this analysis boundary analysis is consistent with conformal invariance. But okay, this is not the end of the story. Let me now do the linearized analysis. Yeah. So here it was like counter term did not depend on phi. Yes.
Because the phi that brings the
yeah.
It's like you have to go to the order until which you need a counter term for
phi. But I mean, you don't have like any more divergence here. Oh, you mean like you should keep the finite term?
No, but you're saying for a general state there are no counter terms for phi.
For general state.
You don't need any. This is the counter term.
Yeah. For this, for the theory we have, and for the solution we are considering. Yeah. So yeah, we don't find counter term which is so okay. It was a bit surprising because it doesn't depend on kappa. Yeah, exactly. Yes. Because we had a scalar field, and then because it was breaking because of this alpha log rho piece. So okay, we did not expect anything in general. I mean, ideally, we hope that we will get something which is consistent with. We wanted a coefficient which is different from -1/3. That could have come from some contribution coming from this scalar. Yeah. Yes. Yeah. Yes. Mm-hmm. Yeah. An alpha. Yeah. Yes. So I mean, so here we don't actually find. So it's here it's not there, but then still we need to resolve this puzzle that okay, I mean we have this logarithmic scalar which is breaking part of isometries. You mean equations? Yeah, this.
The expectation of OX here is not
in the presence of sources. Yeah.
So this just says that the expectation of PA is just expression of
in flat space. Yes. Yeah. Yes. Yeah.
The expectation of PA is not zero, but that's because there is an operator.
Yeah. So, sorry? Mm-hmm. Yeah. Mm-hmm. Yeah, some row. You mean the phi term, F1 term? Or yeah, so that actually I mean actually it doesn't give any contribution in this case. Yeah, I think no, you can do the power counting, and I think from there you can see. Yeah. Yeah. Yes.
What happens is that this term you have to continue the alpha square term to cancel the alpha square first one.
Yeah. There are of course some cancellations. Yes.
is derivative with a very strong derivative. Square root d derivative.
No, but okay, then there will also be rho and rho square pieces coming from this expansion. Okay, so there will also be rho from this. So that also you need to take into account. Oh, so yeah, phi just alpha log rho plus kappa. Plus kappa. Yeah, this one. In pure gravity, yeah. So that was a little surprising because, but it seems it's a special property of this particular vacuum. There are various cancellations, and okay, all these factors of rho also combine. So. Yeah, so okay. So from anomalies, we don't see this thing. And okay, but let's consider this linearized analysis. And so as I mentioned, so to compute the exact, I mean, 2-point function, we need to like fix this kappa 4 or this G4, which were undetermined from the boundary analysis. So that, so since we are only interested in 2-point, we can just study linearized perturbation, and the value which we determine for kappa 4 and G4 from linearized perturbation, that will be sufficient for 2-point function. So we write the perturbation around the background solution in this way. So we had 1/4 rho square d rho square. So we perturb it by writing plus 2 theta. Then we have this 2bi dxi d rho. And then we perturb this 1/rho eta ij plus s tilde ij dxi dxj. And phi is again, it's just alpha log rho plus some more phi, so which is like which will be kappa. So the variables theta, bi, s tilde ij, and phi are small fluctuations, and it is convenient to decompose this bi and hij, which is, yeah, I mean, these things in irreducible transverse traceless parts. So this is analogous to what one does in cosmological perturbation theory. So we write bi as del I nu plus nu I, s tilde ij, which appeared here as minus 2 psi eta ij plus 2 del I del j chi, del I wj plus del j wi plus ht ij. And here nu I and wi are transverse, and htij is transverse and traceless. The metric and the scalar perturbations, one can do a simple counting that they have d plus 1 by 2 plus 1 degrees of freedom, but only d minus 1 by 2 plus 1 of these are physical due to coordinate invariance. So it will be convenient to work with the physical coordinate invariant degrees of freedom. And so one needs to obtain the gauge invariant combinations of or diffeomorphism invariant combinations made out of these variables, and this can be easily done if we note that under infinitesimal coordinate transformation, x mu going to x mu minus some xi mu, the linearized changes in metric and the scalar deformations are given by this. And here also we can decompose this parameter xi I in transverse traceless part in this way, and if we do that, then we find that the various irreducible components transform in this way. And from once we have these transformation, we can find a linear combination of these such that the total combination doesn't transform under diffeomorphism. And these are the combinations. So S1 is say nu minus 1/rho del rho chi minus psi by 2 rho. S2 is theta minus del rho psi by 2 rho. And then you have R is phi bar phi minus 2 alpha psi. And then you have a vector combination. And HTIJ T was invariant by itself. One can also take linear combination of these variables, and some other, in fact, we find that some other gauge invariant combinations are more useful, like this one S2 minus 1/4 alpha rho del rho R. So we shall be working with these gauge invariant combinations because it. So we can write down the now linearized scalar equation under this perturbation, which I just described, and express the equation in terms of this gauge invariant variables, and the equation of motion turns out to be this. And for the metric equations of motion, again, we can do the same analysis, and different metric components can be expressed in terms of these gauge invariant combinations. And so next, so once we have the equation of motion, we would like to solve them. But before solving these, let me consider the quadratic equations of quadratic action describing these fluctuations. So the action for these fluctuating degrees of freedom can be obtained by directly varying the action and keeping terms up to the quadratic order. Alternatively, we can, since we have computed the equation of motion, we can use these equations of motion to write down the quadratic action. And so, so to do this, one notes that the variation of the action can be written, can be expressed in this form, where this E mu nu, so E rho rho, E I rho, E ij are different components of the linearized metric equation, and E1 is the linearized scalar equation. This delta G, delta phi are the this fluctuations of the metric and scalar field. So the variation of action can be written in terms of these equations of motion and perturbation in this way. And now, since we already know the equations of motion, one can express this delta S2 in this form. And with some algebra, one can express this integrand as a total variation. And this allows us to read the quadratic action S2 for the fluctuating degrees of freedom. And this turns out to be this. So this action describes the fluctuating degrees of freedom. And now one, okay, so here again, we find that this is, if you do the isometry transformations corresponding to scale invariance, we find that it is invariant. But if we do isometry transformation corresponding to spatial conformal transformation, we find it is not invariant. So this is another, which F1? Oh, but F1 value we had in terms of this m square by 16 alpha square. It should be there. No, wait. So actually, this is there in these combinations, like here. No, but oh, you mean? Sorry, you mean here? Yeah, but in the in these combinations there is alpha. This in this yeah, gauge invariant there is one alpha here. Yes. Yeah. So, okay, so next let me consider this 2-point function. And so as I mentioned, to obtain the 2-point function, we need to determine these functions kappa 4 and G4, which were not fixed from the near boundary analysis. And for 2-point function, it is enough to solve this using linearized equation. We shall work in momentum space, so we can Fourier transform any function f of rho x in this way. So hatted quantities will denote the momentum space counterparts. And so for solving the equation of motion, we start with the scalar equation. So we had scalar equation so it can be written down in a momentum space, and it is just this, and it gives a simple solution. So S4 is given by this sum C hat K times rho to the power D minus 4 by 2. C hat K is an arbitrary function. So because here it's this equation of motion only depends on the rho derivative. So there can in principle be something which depends on X. So, and in momentum space on K. So this is an arbitrary function. And in fact, this is what leads to all the problems. So, and using this solution for S4, in the Einstein equation, we can find the solution of the other variables from the linearized equations. And so for the non-zero momentum mode, so when k square is not 0, we find this solution. And okay, this r hat depends on another constant b hat k. So we have in principle this c hat k and this b hat k, which are not fixed. So now our holographic renormalization analysis was in the Pfefferman-Graham gauge. Hence, to compute the 2-point function using that analysis, we need to specialize the linearized solution to Pfefferman-Graham gauge. But since we have worked with gauge invariant combination, we can specialize to any gauge, and in particular to the Pfefferman-Graham gauge. And going to Pfefferman-Graham gauge amounts to setting theta and bi in the perturbation. So if I go back, so if we set theta and bi to 0 in this perturbation, we are in the Pfefferman-Graham gauge. So if we can set theta and bi in these combinations, and then we will get the solution in the Pfefferman-Graham gauge, and that is so we can set theta and bi to 0 to get the Pfefferman-Graham result, and setting these fields to 0 and using the solutions of the gauge invariant variable, we find that the solution of various non-zero fields which appeared in the perturbations are given by this. So we had like this phi hat, so it is given by this combination here. Then we had psi, wi, which are constant now, rho independent, and then we had chi. For us, this phi will be relevant because this is what was the fluctuation of the scalar field alpha log rho plus, we had written it alpha log rho plus phi, and its solution is this. So we can compare, you mean this? Yeah, so these were in the H tilde ij, the boundary. Yeah, scalar modes, yes, scalar modes of the metric. Chi, delta ij psi, yes. So we had this 1-point function, which was in terms of, which we obtained in terms of these near boundary analysis, kappa 4, kappa 2, and so on. And differentiating it again with respect to the boundary source will give us the 2-point function O. However, we note that the 2-point function now, so it depends on this kappa 4, which is the, so this kappa 4 is the web for this boundary operator OX. But since, so kappa 4, again, okay, let's recall that kappa 4, so kappa expansion is this. Kappa 4 was the coefficient of this rho square piece. But if we compare it with the solution of phi hat, which we just obtained in d equal to 4 here, so we see that this kappa 0 equal to, so if we compare, then this phi 0 is given by this kappa 0. So so this plays the role of the boundary source, and the coefficient of the rho square, which gives kappa 4, so that gets determined in terms of this c hat. So this kappa 4 equal to minus 2 alpha c hat is what is the web. But since kappa 4 involves this arbitrary function c hat k, the 2-point function will also involve this arbitrary function. So this means that the 2-point function will not have the property expected for the 2-point function in a scale invariant theory. The expected momentum space 2-point function should have power law behavior. But since c is an undetermined function here, it we don't get this to so yeah, okay. So but this is in general, right? I mean, if you consider any like theory, if you do this near boundary analysis, yeah, so okay, what you can do, so okay, let's go back here. So we had this 1-point function of OX. Suppose we were just interested in the 1-point function, not in like 2-point function. So we would, what we would do is we would set the sources to 0. So we will set kappa 0 to 0 and G0 to 0. Now in this kappa 2, G2, they are also, and kappa 2. So all these 3 terms are given in terms of boundary data, which is G0 and kappa 0, which were the sources. So if we set these sources to 0, we will just get this OA of X as it will be proportional to kappa 4. So in that sense, it is the web.
Yeah, that makes sense. You are not breaking it by starting on sources in the boundary.
No, yeah. So this is in fact this is a general result from this Pfefferman-Graham analysis that
And the scale invariance result that you can see.
from no yeah, so that's the so you mean because the 2-point function depends on this c hat k. So for example, in d equal to 4, if c hat k were like some k to the power 4, that is the expected like scaling. Sorry.
It is said c hat k equal to 0.
Okay, then no, but then then this becomes 0. But because c hat k is arbitrary, and this is you need like some particular power law behavior for scale invariant correlators. Yeah. Yeah. No, so you need like k to the power 4 behavior, that explicit behavior. Then you get oh, you mean conformal? No, you get scale invariant, but okay, it's still not clear because the vacuum breaks this isometry. The anomaly is consistent with it has -1/3. Yeah. 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 So at the level of 2-point function, so what you can, so okay, let's consider in a generic conformal field theory, the 2-point function is fixed to be 1 over x to the power 2 delta, right? So this is, but and the role of special conformal transformation is to make the two operators have the same this conformal dimension. So here, if you get like k to the power 4, then you can argue that okay, it's consistent with the like special conformal invariance. But yeah, here, yeah, same operators. Yes, it's already the same operator. Yes, yeah. 3-point function. Yes. Yeah. Okay.
You have to take that derivative with respect to defined scalars.
Yeah, but we don't. We have only one scalar. Or okay, one could come. Yeah, I mean, one could consider the 2-point function of say stress tensor or okay t times o. Will not be, yeah, okay, yes, it will not distinguish. Yeah. But I mean, here it's even worse. But that will vanish, no? In a conformal field theory, it will vanish. But yeah, then it will not vanish. Yes, yeah. Yeah. So so in fact, if we compute something like t times o, and if we find it to be non-zero, then yeah, I mean, say yeah, t mu mu times yeah. Oh yes, yeah. But this c hat will again appear. So yeah. Right. No, but but two operators, yes. Then it will be different. Yeah. Dimensions, yes. Is yeah. So that is one way to distinguish between scale and
but this analysis doesn't do it.
Yeah. So this is still in like some work progress. So this is this story of 2-point function. But let me.
Do you have sets you have k equal to 0?
So this is one solution, but this is a very specific solution. This is like specializing.
But for that solution, the 2-point function at least will have the property of a scale invariant.
Yeah, I mean, so in principle we could, because c hat k is arbitrary, so we could in principle take it to be say 0 or k to the power 4. But I mean, but it's not fixed, right? I mean, this is choosing by hand. Yeah.
Question is it possible to give it a random
consistent with yeah, so that's I think is possible. But as you I think as we just discussed, I think to distinguish between like scale and conformal, we need like different either 2-point function or a 3-point function, not from the O.
Possible that suppose you make one function consistent with scale invariance or conformal invariance. The way we space. Then you go to 3-point function.
Okay. Yeah.
Will you try it?
So in general, we do expect, so if 2-point function is non-zero, then okay, we expect 3-point function. In general, it will be non-zero unless we choose some specific value. But yeah, it's hard to see. Yeah.
From the solution.
Yeah.
It looks like that it's not possible to find a solution which has the full conformal. Right?
Yes. So you mean like, but I did not say, yeah.
The log row, it looks like it's not possible to find a
conformal invariant solution. Yes. Yeah.
Now at least we are finding a case where the 2-point function looks like as if the conformal.
No, but still it's not clear from this analysis, right? I mean, because unless we, so you mean like if you choose a specific value of this thing, but here we cannot really distinguish between scale invariance and conformal invariance because it's same operator. So unless, I mean, if we compute like some 2 different operators, I mean 2-point function of 2 different operators.
One you are saying doesn't even have scale. Right?
Yeah.
From the argument that in earlier, like scale invariance or not.
Yeah, so that is the puzzle. I mean, so this is the something it has to be resolved. But so an anomaly was also not consistent with like scale invariance. But the background we are considering that breaks this isometry. But the anomaly is consistent with having just conformal invariance. So that is what is all this puzzle. But then, so okay, but then there is something else. People have studied this Einstein-Horndeski theory, and here. So when we were writing the paper, actually we found this result, but that here they claim. So they analyzed this theory. This is a specific case of the theory we started with, which has all these 10 parameters. So here, so you have this Einstein-Hilbert term, you have this cosmological constant term, scalar kinetic term. Then you have this R mu nu, del mu chi, and then R, G mu nu, del mu chi. So these are the 2 terms. These were like F4 and F5 in our earlier analysis, the interaction with which we started. And these are the boundary term for this theory. This theory also admits the similar solution. So you can have this conformal vacuum, standard conformal vacuum, but again you can have similar solution, this chi equal to chi s log rho. Now with this different value of gamma and lambda. So in this, so one can do the similar analysis in this theory, and what one finds is that okay, it is been claimed that this while anomaly contains an additional R square piece in addition to the standard conformal anomaly, and the 2-point function they claim is given by this. But what appears, we are still checking their calculation, but what appears is that they have made a specific choice of this C hat of K. If we do that, of course, then we can also get this kind of thing. But it doesn't gets fixed from the equations of motion. So one way, so one thing is to resolve this thing, but same way, yeah. They computed the counter terms and yeah. Yes. In this case, it and also because you can see that here this scalar term involves this R also here. Somehow that it seems it plays a role. But the surprising thing is, I mean, because we can so we started with this kind of theory where we had more terms in addition to just these two. But then we did a field redefinition and went back to theory containing just F1. So we can also do the field redefinition from our theory to this theory or from this theory to our theory. So I will just now describe this field redefinition. So we can map these two theory with a field redefinition. So let me just briefly describe this general procedure. And now I am towards the end. So we can map the theory we have worked with to the Horndeski theory via field redefinition. So let's begin with a brief review of the general procedure. So if we are working at a fixed order in perturbation theory, then we can eliminate those terms in the Lagrangian, which are proportional to the lowest order equations of motion. So more precisely, we can use a field redefinition to transfer these terms to higher order in the perturbation theory. So suppose you have an action S of phi involving a generic field phi, in which terms of different orders are parameterized by some parameter epsilon. So you have S of phi, which is given by S naught phi plus epsilon S1 plus epsilon square S2 and so on. Now suppose at order epsilon to the power n, this Sn includes a term, some say curly b hat bn, which is proportional to the lowest order equation of motion. So suppose bn has this form, integral d dx, some function f of x, which can be an arbitrary function of field and its derivative, and then the equation of lowest order equation of motion delta s naught by delta phi. So if we now make a field redefinition, phi of x going to some phi tilde x equal to phi x minus epsilon to the power n f of x. And if we do this field redefinition in the original action here, then we see that because this field redefinition involves epsilon to the power n, so any change coming from S1, S2 and so on, it will be of the order epsilon to the power n plus 1 and higher. So those we can ignore. But there will be one term coming from S naught phi, which will be of the order epsilon to the power n. And this will precisely cancel this bn term. So this is the general philosophy of field redefinition, that if we have some term in higher derivative terms, which is proportional to equation of motion, we can eliminate those terms by this kind of field redefinition. And the field redefinition involves, as we see, this coefficient of equation of motion, this f of x. So, so the general action we started with had this form. So, okay, I have ignored the y terms, but if we consider other terms, they had this form. And the lowest order equations of motion imply the value of box phi r and r mu nu can be expressed in terms of this lowest order equation of motion, say del L0 by del phi, del L0 by del g mu nu, and so on. So we can substitute, say, box phi r mu nu here. And then we can read off this function f of x. If we can express this higher order term in this form, then we can read f of x. And so if we do that, then this gives this field redefinition. So this is okay. We have worked with for the general action, this one, which led to just F1 term. So if we, so it involves all these higher order couplings. So for example, phi involves these field redefinitions. Phi prime minus, it depends on F2, F6, F3, F6, and so on. And similarly, G mu nu has this complicated behavior. So if we make this field redefinition, we are left with this action with which, I mean, we have worked. And now in this theory, the parameters m prime u and f1 prime, they can be related to the old parameters in this way. And so we had worked with this theory, but it's possible to go back and forth between these two theories. Yeah.
The solution that we had, the scaling variance solution.
Mm-hmm.
Does it does this field go to identity? It has to conformal or not? Does it act on the
No, so I did not understand. So you are saying I start with the vacuum we have. We make the field, say this kind of field definition. This one? Yeah, this is normalizable.
but does it change the boundary matrix?
No, so actually, so we will see one example of this when we map to Horndeski theory. So it actually doesn't change the so it only changes the scale. So like the cosmological constant of the space-time. So it changes the length scale of the metric. So in this particular example, I mean, for this Horndeski theory, but in general, we have not, okay, I mean, we have not analyzed the in full glory all the possible terms. But in principle, it's probably possible because there are, you can see that there are many terms depending on okay, R, box phi and so on. So in principle, okay, if we probably include all the terms, then okay, it's possible what you are saying. But since we were only interested in mapping it to this Einstein-Horndeski theory, we find that okay, it just changes the scale. So in fact, yeah, this is what we are currently doing. We don't expect, yeah. So essentially, okay, this is yeah. The calculation is still not complete. So yeah. But we don't expect that anomaly will change. Okay. But you. Yeah. Okay. I mean, if one back of the envelope calculation, if you do for this just divergent part, if you do this calculation, you find that this log piece, log epsilon piece, that doesn't change, which is what was responsible for anomaly under this for the Horndeski theory. So that is why, I mean, it looked very difficult that anomalies can change. No, but counter term depended on that term. That. Okay.
The divergence is not really that.
Yeah. Yes. Yeah. Yes. Yeah. Yeah.
That's not really the case.
Right. Okay. Yeah. So here, okay, it's okay. Once I think it doesn't look, but okay. I mean, because they claim that there is a different anomaly, so it should be possible unless there is a mistake. So let's me.
What I'm saying that it's possible that their systems has the anomaly, but that can be improved.
Okay. Okay. So that needs to be checked. Yeah.
Maybe that improvement is what is done with
Yeah. But still, it doesn't resolve this issue of the vacuum is breaking this isometry part of the isometries. So it should be consistent with the 2-point function and so on. So that also needs to be resolved. So one can do the inverse field redefinition. So once we have the full field redefinition, we can do the inverse field redefinition to go back from the Horndeski theory to this theory containing F1, or sorry, the other way. So we can also map the boundary terms. So the boundary term in the theory, which had only F1, had the standard this Hawking-Gibbons-York term. But if you do this field redefinition and in the F1 action, together with this boundary term, then it generates this boundary term. And now, since we know the form of this delta G mu nu and delta phi, which is these pieces, so if you do that, you can generate all possible boundary terms of these general theories, which had all the higher derivative terms. And this, it is expected that this theory will have lots of boundary terms because there were many this Riemann tensor terms. So there are lots of boundary terms in this. But the good thing is, we find that if we do this field redefinition and just contain F4 and F5, we precisely obtain the boundary term they had. So this F4 and F5 pieces, if we just fix, so if we choose F4 and F5 to be these values, then we precisely obtain this Einstein-Horndeski theory from our F1 theory by this field redefinition. So to conclude, so we analyzed the 2-point function in the 4-derivative effective theory containing gravity and the scalar field. This theory admits the scale invariant vacuum along with the standard conformal vacuum. However, it does not appear to be consistent with the expectation from 2-point function and anomaly. And this puzzle arises because we can map our theory to Einstein-Horndeski theory, which also admits these 2 vacua and is claimed to have correct 2-point function and anomaly. And okay, it's still work in progress. So thank you.
Are there any questions? If there are any, yeah. Thank you.
Thank you. Yeah. So I will leave. I will leave tomorrow morning. So I will see you sometime. Yeah.
So you mean like this?
But that is still, so anomaly is more like it's a statement about the particular vacuum you are in, right?